Hey, good evening. So this is Mayank Parekh, and I will be your instructor for this course, which is starting today. So before we start that, I just wanted to walk you through how to navigate through the course site. So when you log in, you'll get something like this, correct? And here, there are pre-recorded classes which have been taken earlier, which you can go and look at it. There are some video lectures available. Then there is course content that is very important. That is what you will regularly see. So every session, I'll be pulling out the presentation from the course content and walking you through the presentation for that particular day. Within the course content, you'll see on the top there are numbers 1 to 10. Now 1 to 10 are the 10 sessions. So we are in session 1. So 1 is highlighted now. If I go on to 2, it'll open up the content for session 2. Now under session 1, you'll see that there is a video called Description of Raspberry Pi Components. There is something called a sense hat. This video describes the sense hat components. Then there is a presentation, which is the presentation for today. Then there could be some assignments and case studies that you need to work on for this particular session. Then very important thing is prerequisites. As you can see, there are 4 different sets of prerequisites. I see that except a few of you, a lot of you don't have any background in Python. So except one person, everyone has done programming, which is welcome because we are going to do programming here. Of course, we'll start slowly and you'll have a lot of time to pick up. So my strong suggestion in the prerequisites, if you go to number 1, in the number 1 is Azure and Azure storage. Number 2, we have some Linux fundamentals. Number 3, your basic Python programming. So every one of you, even if you know Python, I request you to go through these videos. They're very useful videos. At least you'll get the basics of Python. Okay. And believe me, Python is very easy to use, very easy to set up. In half an hour, you'll be up and running on your any type of Mac or Linux or Windows desktop or notebook or laptop. So set it up on your machines, start experiment. There are a huge amount of videos available on the net also. These videos are very good, but if you're more interested, go and find out. And it's very easy to use. So what I will do is, since a lot of you don't know Python, the initial Python programs I'll walk through very slowly. And then slowly we will increase the pace as you get the Python understanding. So first thing I want you to do is Python as a prerequisite. So number 3 in our prerequisites is Python, which you need to do number 1. First thing you need to do. Then number 2 is Linux fundamentals. Go through that. It'll be very useful because when you work with Raspberry Pi, the operating system is Raspbian. So you'll need to use it consistently, which is nothing but Linux. It's a Debian port of Linux, which is called specifically for Raspberry Pi. It's called Raspbian, and which I'm going to walk you through how to set it up on a Raspberry Pi tomorrow. So go through that. That'll be very useful. Then after this two, then you can go through the number 1, which is Azure. So go through that. This you will need before our 5th session. So in the 5th session, we are going to start on Azure. So you got sufficient time. You got 3 weeks to cover that. So cover that part. And then last thing you should do is the Power BI stream, though it's not necessary, but we are going to do some work in Power BI. So it's a very interesting area and there are only 2 videos. So just go through that. Very interesting videos are there. Okay. So that's about the prerequisite that I wanted to cover. Now some rules of the road. We are having this session, each of them lasting for 3 hours. So today we are going to do introduction of Internet of Things. I'm going to talk about what are sensors, what are actuators, what is Internet of Things, how does everything fall into place, how does information flow into a typical Internet of Things application or a solution. Okay. Then we are going to talk about something called as the architectural blueprint. So if you are developing an Internet of Things applications, then what are the things you need to look at? So there is something called as a blueprint, which you can use as a template to start analyzing and then making some decisions on how your project is going to be. So for those of you who are a part of IoT projects or who are going to be a part of them or you want to be a part of it. Okay, so I'm going to talk about quite a bit of stuff here. Then we are going to talk about what are the different types of boards like Raspberry Pi. We have a friend who has done, a couple of folks who have done Arduino today. So Arduino, Raspberry Pi, Intel Edison board. So we're going to talk a little bit about that. Then I'm going to talk about a little bit more about the Raspberry Pi, what exactly this board is and why we have chosen Raspberry Pi as a device for our course. Okay. And then we are going to talk about Sense Hat, which is a set of sensors. And when we talk about the Internet of Things application solution today, you'll understand where the sensors fit in. And then we are going to use a Sense Hat along with the Raspberry Pi. So there are 2 things you may want to buy. One is Raspberry Pi and second is sense hat. But it's okay if you don't buy a sense hat. Raspberry Pi should be enough. If you don't buy sense hat, we will use simulators for sense hat. The simulators will simulate as if there is a sensor instead of a sensor, which should do its job without actually using it. So it's okay. So that's what we're going to cover today in the session number one. Session number two, we are going to set up the Raspberry Pi and sensors. So I'm going to walk you through the whole process of, first of all, from scratch. How do you set up the Raspberry Pi? After that, we are going to talk of some very important stuff, like how do you remotely access your Raspberry Pi? Because a Raspberry Pi is a very small device. It's like a small rectangular box, very small, a little larger than your playing card box. Your playing cards are there. If you put it in a box, it's some little bigger than that. That's the size of a Raspberry Pi. It doesn't have a monitor, it doesn't have a keyboard, it doesn't have a mouse. But after you set it up once, then you can access it remotely from your laptop. So I hardly use my Raspberry Pi with a monitor and keyboard. I put it on and I'll remotely access it through my laptop. So it makes it very easy, that's why it's very portable. And then in the second session, after showing you that, we'll work on some very simple, very start, basic, I would call hello world of the Python programs. We'll start with that so that you get a taste of what Python is. Very, very simple approach to that. Then the third session will be creating solutions with Raspberry Pi and SenseNet. Session number 4, we are going to talk about communication protocol. Session number 5, we are going to talk of IoT and cloud computing. Session number 6, we are going to talk about Azure solutions. So we are going to practically start some solutions on Azure straight away. In session number 7, we are going to do very interesting stuff. So we are going to do Power BI, we are going to do remote monitoring, all IoT. So these are completely end-to-end IoT projects, but we'll slowly will build up on that. Session number 8, we are going to talk about something called as edge computing and analytics. So by that session number 8, we should be very comfortable with Azure. Okay. And session number 9 and 10, we are going to do 2 projects. One is a presence detector, how you detect the presence of person or anything. And the session number 10 is we are going to build a Twitter bot. Okay, so this is our overall curriculum, what we are going to cover. So today we're going to do introduction to Internet of Things, and what are we going to cover? So I'll explain what is IoT. I'll map the IoT process flow. So typically how information flows. Then we understand the IoT architecture, and we'll talk about the decision framework, the blueprint I talked about. Okay, then we talk about the development boards, and then we talk about sensors, and in particular the Sense Hat board. Okay, we'll talk about it today. So this picture, I think all of us would have come across some different things like this, right? Some of the, so using a mobile phone to put on or off a light, or the one in the center top. It's like through a remote control, you're accessing or setting the lights, or now you would have seen in some hotels offer that also, that you're able to control certain things within your house from the far off location, from your office or wherever you are. Then we have something called as this Fitbits. We have those medical devices. The person on the finger measures the oxygen in the blood and the heart rate. Then on the right side bottom, you see a car. So it's a connected car concept. So what is all this? What are the technologies behind that? So everything, everywhere, there is some sensor which extracts some data or information from the environment, passes it on to somewhere in the cloud. Then there are some applications which understand that data and then use that data to control back or do some analysis on that. So that's the overall the way IoT works. So basically all this behind the scenes is nothing but Internet of Things. Internet, we all know, right? It's a term given to the network that is formed by connecting computers and the thing. So when you expand the capability of the internet from connecting computers, today what is happening? Only thing that is connected to the internet is computers. But then there are very small sensors. So I want to, let's say you are in your office. Generally, all of us have gone through this. Either, in the winter within the office, it gets very cold, so you have to wear sweaters. And maybe in the summers, the temperature you feel should be more cold. It is not as cold, it should be cool as it should be. Or if you go in a meeting room to a customer location, sometimes the meeting rooms are very cold and sometimes they're very uncomfortable. Why is it like that? Because then the situation is there should be some sensors. The sensors are sending some data, but then the connectivity and the information analysis from the sensors is not being done in a correct way. Just like computers, but when you connect sensors and there are several small electronic devices, then you call Internet of Things. But if you talk of computers, how many computers will it be? So you take out the number of the population, that's the maximum number of machines that can perhaps, maybe a little more, something like that. When you talk of sensors, there are billions and billions of sensors that can be connected. And if you have heard, the next set of hacks are going to happen through devices or sensors, not humans. Why? Because if devices can be connected, then why will I waste my effort only as the one person doing something? As an hacker, he will have many devices, many small sensors, hacking anything he wants in a very coordinated fashion. Correct. So basically, Internet of Things is nothing but sort of computers. When you connect a lot of several small electronic devices, an Internet of Things is formed. So the internet plus the thing is what we call as the interconnected network of physical objects and virtual components, which has the ability to sense, communicate over a network, and share information with each other is known as Internet of Things. Okay, this is a definition, but the intuitive way of looking at it, there are sensors. Sensors are nothing, but they give us information about the real world. What does that mean? So if I want to know the temperature, there's a temperature sensor. If I want to know the quantum of light, there's a light sensor. If I want to know how much current is flowing, there is a sensor which can measure that. If I want to know the orientation, I mean, horizontal, vertical, so there's sensors to do that. So there are sensors which can detect pollution. There are sensors which can detect gas. There are sensors which can detect water flow. There are acoustic sensors. So all this, what these sensors do, they basically tell you something about the real world. They can sense the real world, and they communicate that information over a network. And then there are some applications which will process that information and take some actions. That complete loop, when it is completed, is called Internet of Things. So where did this come from? There's a gentleman called Kevin Ashton. In 2009, he wrote an article when he was working for our presentation he made to Procter and Gamble. And that's where unknowingly he coined the phrase Internet of Things. At that time, it was connecting RFIDs. And RFIDs, it's heavily used in supply chain today, like the Walmarts of the world, they use RFIDs heavily. So somehow, that stuck. So you can read this article. It's an interesting article, small thing that he says, but that's where the word Internet of Things got stuck. It's a nice term because it really signifies what actually is happening. So what is IoT and M2M? What are the differences between that? So we'll check out. Basically, M2M is, it refers to isolated instances of device to device communication. So it's a very specific subset of Internet of Things. So Internet of Things is many things but connected through internet. It's not just device to device. Here M2M is device to device, machine to machine communication. Okay. So M2M is, you can say, is a little specific case of Internet of Things. Would you really use this information? Not exactly, but it's good to know because sometimes people use this term interchangeably. So you don't need to know what M2M means. So point-to-point communication usually embedded within hardware at the customer site, whereas Internet of Things is communication through IP networks. Now, machine to machine is largely devices use cellular wired networks. Internet of Things, data delivery is through multiple channels or through a middle layer hosted in the cloud. M2M, you don't need an internet connection because just two machines talking to each other. In most of the cases, IoT will require an active internet connection. Because M2M is very specific between two machines, there are limited integration options. It's very specific to different types of devices that are connected, whereas Internet of Things follows some open standards. So there are unlimited integration options. You can integrate any type of device today to any type of cloud, or you can create data from anywhere in the world. And then you can analyze it and take control, and perhaps like we see how Google uses it so nicely, Google Maps. Have you ever wondered how Google is able to give you the current situation on the road so beautifully, that the traffic is there and suddenly as you see the traffic is dispersing, the color change from red to yellow or yellow to blue? Why is Google able to do that? Google itself won't be able to do that. It's us. Unless we provide the data to Google, Google can't do it. So when I'm using Google Maps, I'm telling Google, okay, I am at this location and this is how I'm the speed at which I'm moving. Now, if I'm stuck, Google knows that there is a jam. Google has the road coordinates, so it understands, okay, not just one car, but five cars in the same road are showing the same sign. That means there is a jam. and suddenly it sees that no, this car has started moving a little better. It was 0, it's 10 kilometers per hour. Then it makes red to yellow. So that's what it is, because, and all of us are different types of devices. Still, it can integrate and can get all the data. That's the power of Internet of Things. So how do we build a solution? There's something called a solution reference architecture, or instead of using such a heavy word, I would rather call it as information flow, not a reference architecture exactly. So it's a four-stage information flow architecture. So IoT is not just internet connected devices. So in fact, IoT is a technology that builds systems capable of autonomously sensing and responding to stimuli. Correct? Google Maps. So automatically, without me knowing, my sensors in my phone are sending the data to Google Cloud. And Google is collecting the data and responding to that data in a dynamic way by updating my maps accordingly. Again, updating the maps based on multiple cars in the same location, sending the traffic information. Correct? So autonomously sensing and responding to stimuli from the real world without human intervention. So beautiful example of IoT is Google Maps. So we therefore need to develop a process flow for a definite framework over which an IoT solution is building. Correct? So in stage one, we have something called as sensors and actuators. So these are little technical terms. People use it interchangeably, and a lot of times your sensors and actuators are combined into one device. So if you look at it granularly, what is a sensor? It is nothing but converting a physical information to a signal. You would have heard of thermistors. What is a thermistor? Thermistor changes the resistance. It's a resistor actually, resistor, but changes the resistance according to temperature. So as the temperature goes high, the resistance goes low, which means the current flow increases across that. So at the end of the day, physical information environment is temperature, and the signal here is okay, the current flow is increased or the resistance has decreased. And what is an actuator? It acts on the signal from the sensor and converts it into a digital sort of an output. So most of the time you'll see sensors and actuators are combined into one entity, and largely this term is used interchangeably. So objects are equipped with sensors and actuators, thus given the ability to emit, accept and process signals. Just like I took an example of thermistor. So any other such thing that comes to your mind, something similar to thermistor, which converts a physical environment information into an electrical signal. Yes, Deepak is right. One is pressure transmitter, correct? You would have heard of photoresistor. So photoresistor is changes the resistance based on the amount of light. So the resistance changes the more the light, the resistance decreases, just like temperature. And a photoresistor is the reverse of a actually functionality wise, not in device wise. What a diode does, LED, light emitting diode, it emits light. So it converts digital signal to a light signal, whereas a photoresistor converts light information into electrical signal. So Harigunda says yes, humidity sensor, correct. Particle count, yes, that also there are semiconductors available which can do that. LDR, correct, light dependent resistor. Piezoelectric, correct. Piezoelectric is actually a pressure sensor. So it changes its signal, electrical signal based on the pressure it is under. They're crystals basically. Piezo crystals are available which can do that. PIR sensor, yes, so proximity sensor. So there are different types of sensors. Some directly convert environment information into electrical signals. Some have multiple steps. So that is about sensors and actuators. A thing in the context of Internet of Things is an entity or physical device that is a unique identifier, an embedded system, and the ability to transfer data over a network. Now see, we are extending the concept of a sensor and actuator. Multiple things here. So first you have a sensor and actuator which convert the physical stimuli to some electrical signal. Now it has a unique identifier. Now we are coming into the world of IoT. So why it needs a unique identifier? There are millions of sensors. Like I talked about the large OEM, let me take the name, it is Maruti. Now they are planning to have connected cars IoT project for about 1 million cars within 5 years. Now if there are 1 million cars, each of the car transmitting the data, then there is to some unique identification, correct? Just like our each of our laptops, if you know, it's got a MAC ID, a network adapter has a unique ID. Like that, every sensor will have a unique ID, correct? So that it does not, you can always distinguish between two sensors. While data is coming from millions of sensors, and you're interpreting, you're analyzing the data, you need to know exactly where it is coming. You need to know whether this car is moving in Hyderabad, or it is moving in Mumbai, or it is moving in Delhi, or it is moving in Bangalore, or in Botswana. And then based on its latitude and longitude, you'll be able to track and monitor that car. Correct? So that is one. So unique identifier. Second is an embedded system. Because at the end of the day, sensor, after some processing of that information, will have to send that data to the cloud or somewhere else to be processed. So it needs some logical capability. So when we say an embedded system, it could be something like an Arduino, or even a PLC can work at a lower level, or something like Raspberry Pi, which is a much full-fledged computer system. Okay, so it needs some processing or some intelligence where you can do some programming and insert some intelligence which can collect the data, maybe do some manipulation of the data. I'll tell you what is the type of manipulation as we go along, because the data from the sensor, sometimes you have to combine data from 5 different sensors and send it as one packet. So that system needs to do all this stuff. So that's why you need an embedded system. And then the ability to transfer data over a network. Then it should be able to have a mechanism to communicate over a network. So all this thing, if we call it as a part of stage one, capabilities. So embedded system is nothing but a microprocessor based device which has an inbuilt operating system. Somewhere operating system could be very, very developed, like Raspberry Pi. They've got a complete Linux operating system. Arduino, it's got a very inbuilt OS embedded system which can interpret program, just flash the program, it'll run the programs in a loop. Or a PLC, you just program the logic controller and it just run that logic every now and then. So OS inside embedded system is designed to perform specific functions that too under a time constraint. And embedded systems are generally systems within systems. Hence, they generally cannot function on their own, but there are exceptions. So typically, as I told you, embedded systems are a part of sensors. So they are not computers by themselves, but they have basic intelligence to do this basic logic of collecting the information and throwing it out on some network. So what are the components of an embedded system? So it's got three main components. So basically it's got hardware. So again, good example is Arduino here. Arduino, or Raspberry Pi, or many such devices are available today which connect to the actual sensors. Then it embeds. So one is the hardware. Second is embeds mean application software. So either you flash it, or you are able to flash it periodically whenever you want it, or it could be hardwired and inbuilt into it like a PLC, or PLC also could be, you could set the logic, and it embeds in real-time operating system. So like Arduino got its own operating system which does a limited set of tasks. It understands what are GPIO pins and everything, and it basically gives you a programming model where you can give your logic and accordingly it takes action. So as we see more of Raspberry Pi, we'll understand that. So these are the three main components. So it's a hardware, some logic that you provide or you flash it, and some underlying embedded operating system. So, you can call every IoT device an embedded system, but not all embedded system IoT devices, correct? Embedded systems can do a lot of stuff, but of course, every IoT device has some embedded, and it need not be in one sensor. So like you get a temperature sensor, which is a dumb sensor. But in stage one, you combine it with something like Arduino or Raspberry Pi, and together they make stage one. Now coming to stage two. The data from the sensor starts in analog form, which needs to be aggregated, converted into digital streams, correct? So data acquisition systems perform this data aggregation and conversion functions. Typically, these are like, once the data is available, you may have 20 different sensors at different locations within a factory or anywhere. But then there's an aggregation system where all this data comes in, and then your sensor may send the data every 1 second. You may not want to analyze the data every 1 second. Some sensor may send every 10 seconds, some sensor may send in 1 minute. But then the aggregation system understands that and collates that data, packages it, and sends only the relevant data to the next level. Okay, so that is called the stage two, which is called the edge, and it starts the communication from here. So stage two systems, typically they sit in close proximity to the sensors and actuators, and sometimes they are called gateways also. So gateways or edge devices. Again, edge devices has a specific meaning. Gateway also has specific meaning, but they are used interchangeably because a lot of time the same device does both the functions. Okay. For example, a pump might contain a half dozen sensors and actuators that feed data into a data aggregation device that also digitizes the data. And an adjacent gateway device or server would then process the data and forward it to stage 3 or 4. Okay? It'll get clearer as we move along. Now stage 3. So we started off with stage one with the information generation from the sensors and creating digital signals and maybe having some basic intelligence to push it to the next level over the network. And stage two, we have some gateway or some more computing power where we can aggregate or analyze or do some basic work before we send the data to the next stage. So we prepare the data, that's called data stage. So it's gateway or an edge device. So stage three, IoT data has been digitized and aggregated. It's ready to cross into the realm of IT. However, the data may require further processing before it enters the data center. So the edge IoT pre-processing system may be located in remote offices or on edge locations. Correct? Like I'll give you a simple example. Like you have a factory where you have a big boiler. Now you have a temperature sensor on the boiler and you need a simple functionality that when the temperature goes above 104, it should notify something so that it can be immediately shut down. So, your stage one and stage two will be the sensor will be a part of the stage one. It pushes on the data to some basic processing device. And then to stage three is again an edge device where it analyzes the data and checks the temperature value. If it is below 104, it discards the data or sends it to the next stage. Above 104, it immediately activates a stepper motor which will go ahead and trigger a shutdown of the boiler. Why? Because the boiler shoots above 104 or 5, then it could be a disaster. So this is called edge analytics. So you did some analysis at the edge, correct? So edge IT processing systems may be located in remote offices or other edge locations, but generally they sit in the facility or location where the sensors reside, closer to the sensor, such as in a wiring closet. Okay. For example, rather than passing on raw vibration data for the pumps, you could aggregate and convert the data, analyze it, and send only projections as to when will each device will fail or need service. Correct? Instead of sending all the data to the cloud, it will only send relevant data. That's what the edge device does. So stage four, now the data that is received needs more in-depth processing, and where feedback doesn't have to be immediate, gets forwarded to physical data center or cloud-based systems where more powerful ITs can analyze, manage, and securely store the data. So multiple things happen. You first store the data that comes in, then you analyze. You analyze based on the history. So you generate the patterns, historical patterns, compare it with the historical patterns, and try and identify if the current pattern is matching with some historical pattern, and if that historical pattern is a failure pattern, an impending failure which can happen sometimes afterwards, then it can immediately raise an alarm saying that perhaps this pattern suggests that this device can fail in an hour. Then that is a field of data science and analytics. Okay, so you want to analyze, and here it is a little deeper analytics, not just temperature is above or below 104. It's identifying the patterns within the data. It's not just single variable. There'll be multiple sets of data coming from multiple different sources, and together they generate different types of patterns. To give you a very simple example, a motor is there, constantly it is sending its data. Now, when you constantly collect the data and you try and see those patterns, now you see that there are some patterns emerging which shows that the inclination of the spindle is little disoriented. Secondly, the vibrations have increased. Third, the temperature is slowly rising. These are all signs that the motor is slowly giving up. But it can so happen that there could be some spurious readings also, isn't it? Which you call as false alarms. So in between it can come, but it does not sustain. Then you don't call it a pattern. So then you see that no, slowly, constantly the vibrations are slowly rising, temperature also very slowly but rising. Then you can definitely identify a set of pattern and say, okay, when it happened last time, after some time, the motor conked off. So here you can do those type of analytics. It's called multivariate analysis or regression analysis if you have understood. But then there are a lot of ways you can do that, but these are some simple techniques. Okay, that's the stage four. So this is the four stage architecture for us. So stage one, sensors, actuators. Stage two, data acquisition systems. Stage three, edge IT, data center. That's all from the sensor. Data moves on to the applications which manages. Still, we are not talking about cloud or anything here. So how do we build a product? So there's a product development roadmap, which we call as the IoT decision framework. And what is the IoT decision framework? It's a grid, which is like on one side you have IoT technology stack, and other side your decision areas. As I told you, IoT is a fairly complex solution. We have to see the complete technology stack, and for each technology stack we have to see all the decision areas. So this is how it looks like. So you see on the horizontal axis at the top, you see the IoT technology stack. We can define, we saw the four stage architecture, correct? We are making into a five stage architecture here. We're changing it a little bit. So device hardware is there, device software is there, communications is there, cloud platform is there, cloud applications here. These are the 5 parts of the technology stack of the IoT. And then each area of the technology stack, you see what is the UX user interface you need for that, what is the data you need or you expect from there, what is the business requirement there, what is the technology behind that part, what is the security, how are you handling security there, how are you managing standards and regulations. So you start with, let's say, hardware. So device hardware, of course, device hardware, you're not too much concerned with the user interface, but of course you want to see what type of data it generates. Is it sufficient for me? Or if that is not, then do I need some? I took an example of motor. If motor is sending me only the vibration data, that may not be sufficient. So I'll need more sensors on that. I'll need temperature also. I'll need the orientation of the spindle also. So what, based on the data I need to define what type of hardware I need in terms of sensors and gateways also, because after the sensor send, what type of gateways I'll need. Business wise, my final goal is to do predictive analytics of how the motor is going to fail. I'm just taking an example of this motor for this to explain this now. So my business goal is predictive. So I want to do some predictive analytics. So how do I do that analytics? Simply said, as I just described, identify different patterns of data. And again, very simply put, I'm analyzing 3 sets of data: vibration, temperature, and orientation of the spindle, motor spindle. I'm constantly seeing the data coming from the motor and seeing their values, how they're changing over a period of time. More or less, within a small range, they will be moving. So far, so good. But my business requirements are, so I want to find when the motor is going to fail. So your data scientist will tell you that I will need these 3 sets of data and I'll analyze it over a period of time. And based on that movement in time, these 3 variables, I'll be able to tell you when it is going to fail. So based on your business requirements, you're going to decide that, okay, I need these 3 variables. And that's how you just give 2 variables, your analysis won't be complete. So, your device hardware is defined by that business requirement. Again, then technology stack. So what is the technology behind your device? Are you going to use dumb sensors? Are you going to use intelligent sensors? Are you going to use in a steel factory where there's very intense conditions? You need robust sensors, as sensors will themselves will wear out. Or do I need these sensors in my office where the conditions are very nice and I don't need very robust sensors? So the type of technology is decided by that. Security regulations. How my data here is going to be used? Is this private data? Can someone hack into this? So taking the example of my motor again, my motor is sending the data, and based on the patterns generated, if a particular set of patterns is identified, my analytics software is going to tell me that this motor is slowly started degrading and in performance and will conk out in 2 hours. Now, let's say just like this motor is sending the data through internet, if someone wants to hack, like XYZ will send some spurious data to the same part of the cloud, impersonating as this motor itself. So instead of this motor, my software thinks that that data which is coming is correct data. And even if though my motor is working fine, some spurious data tells that, the motor is going to conk out, and what is going to happen? It sends wrong signals that this motor is going to go back. So is it secure? How do you secure it? You have to do that analysis. Standards and regulations. You must have a lot of standards and regulations these days, correct? So in European Union, privacy data, it's a big thing. You can't take private data out. You can't do a lot of things with that. Even if you use it for something, you have to take permission from the end user. So just like I talked about the device hardware in the perspective of all the 6 decision areas, you'll talk about device software, the communication, the cloud platform, like whether to use cloud platform. Should I use Azure? Should I use a private cloud? Because let's say if it's a nuclear center and I'm doing some Internet of Things in, let's say, Bhabha Atomic Research Center, which is a nuclear center facility within India near Mumbai. Do you think the data from that is going to go to an Azure cloud or an IBM cloud or a Google cloud? No, because that data is so private. So it'll need a private cloud. It can't use any public cloud. It has to be a cloud which is in their own premises. So my cloud platform is decided whether I can use. So first of all, privacy issues can be there, security issues could be there. Thirdly, certain clouds may provide certain capabilities, certain cloud may not provide. So a cloud platform decision will be taken based on that. And then your cloud applications also. Again, your cloud applications could be of multiple types. What are you going to do with this data? First of all, you want to store. So you'll need some data storage. It could be your object storage. It could be your, NoSQL storage like MongoDB, or it could be a SQL storage like an Oracle or a SQL Server or a MySQL or a PHP or a PostgreSQL database. Secondly, it can do analytics, which is visual analytics, It needs to draw some dashboards and all that. So what type of applications? So how do I write these applications? Will I develop them? Or if I want to only visualize it, can I use Power BI or something which is available out the shelf? So those are the applications you have to take decisions. So that is called the decision framework. For each area of the technology stack, you will run through each of the 6 decision areas and make some decisions based on that. So as an architect, as a part of the team who's developing any IoT solution, this is what you need to do. Before you even embark, you need to come up with a decision blueprint, as we call it. This is how you see the difference between an architecture of a regular software or an IoT software. Huge difference, correct? Here you're talking of device software, then you're talking of device hardware, device software, communication channels. So there are multiple ways of communicating. So your sensor connects to your gateway maybe through hardwire. Like our sense hat is going to connect to our Raspberry Pi using simply GPIO pins, which is hardwired. Somewhere you'll see it is using Bluetooth. Somewhere if within a factory area, it could be like across an acre. So you'll use some technologies like LoRa. You would have heard of LoRa, LoRa or LPWAN. So they are long and short range, transmission communication protocols. And from there, then you use the internet to send it. So a lot of communication decisions need to be made. Correct. So you will use this technology stack at decision areas and then come up with a architectural blueprint. Okay. You see this IoT technology stack. Correct. We discussed each of them: device hardware, device software. We talked about communications. We talked about the cloud platform. Correct. How we are going to decide. We talked about the cloud applications. I took examples and explained you this. Okay. You can go through this, get a little different perspective when you go through the slides. And then you go through each of this technology stack using each decision area. And that's why we saw that matrix, correct? So user experience, this is what you're going to see and what you're going to decide. Data, very important part. Where you're going to store, how much you're going to store. On the cloud, the data costs. So as you go on adding data to the cloud, the cost go on increasing. So you have to see how much to retain, how much not to retain. So there are two aspects to that. First of all, do I need to send all the data? So you're getting the data from the motor, let's say every 1 second. So I'll give you an example, very simple example to give you how huge the data becomes. So I was involved with one project with a large wind power company in India. You know those windmills, right? Those large windmills, those white colored, big pole, and then you see that fan like thing at the top. And typically it is into areas which is fully open, like, deserts or very open areas, so that there's a lot of wind is full over there. There is a company which had such 40 locations within India, and each location approximately that 50 windmills. And you would have seen those pictures, right? All these windmills standing in a line. And what are the basic business goal? They wanted to make sure that their wind power generation, which for current lot of reasons, there is some losses in the wind power generation. So they wanted to improve on that and generate 10% more power. So to lessen or to minimize the losses. And why do the losses occur? See, these windmills, they are constantly rotating, correct? Harsh conditions, heat and wind. So they slowly change their orientation. The motor becomes some loose. And that's why they need to be at the right angle, right position to generate the maximum amount of capacity power. So what they did was, for each windmill, we designed around 100 different types of sensors. Now each sensor is sending very little data. It's on 10, 20 bytes of data. But you look at it, there are 40 locations with 50 windmills, so 2000 windmills, each having 100 sensors, or 200,000 sensors. Every sensor, let's say, even if it sends 10 bytes of data per second, then per minute, it'll send 60 into 10, 600 bytes. And per hour, it'll be 600 into 60, 36,000, or 36 kilobytes per hour. This is only from one sensor. If you calculate this way for all the 200,000 sensors, it comes to terabytes of data per day. Now, are you going to store all that data into the cloud? Every day, terabyte of data, you know what it costs? I'm sure some of you would have gone and seen. I'll show you in Azure what are the prices of that. It costs a fortune. So you don't want to store. So you decide what data to store where. Again, how much in object storage, cheap storage. So all the decisions, I took a little longer example, but it gives you practical flavor. That's why I took this example. So there are decisions you make on data. Then business goals and business decisions, they're the most important thing. Everything is decided using what is the business goal. At the end of the day, there is no business, like I told you in this windmill scenario. Their goal was to generate 10% more power. That's it. That was the business goal. Everything was moving towards that. Then the technology. So what are the technology used in each layer of the stack? Correct? And then security. I talked about security aspects, and again at each layer, not just at sensor layer. That each layer security is to be taken care of. And then the standards and regulations. Absolutely important because IoT applications today are across the world. So there are organizations which have this multiple geographically distributed setups. The sensors are across the board. The data coming from multiple countries. Some countries have different regulations, some countries have different regulations. You need to ensure that you follow all the regulations. Okay? So that's about the blueprint. Now we'll go on to the development board. So now we are going to talk about what type of device hardware and specifically the one that we are going to choose. So, typically all these are available as development boards. And when you say development board, for those of you who have gone through that, always consists of one microprocessor, similar to what we have on our phone. So sometimes from the same companies, it's got some minimum programming support, and then it contains little or no hardware for user interface. Most of the time, the boards will come with connectors for that, which means they'll support, but they may not have any interface connector. Like Arduino does not come with a typical interface, whereas Raspberry Pi comes with a HDMI output, which you can connect your monitor or TV. So the most important uses are to serve as a method to program application inside the product. So it's like simulating your embedded sensors. You can connect sensors and then you can define the logic within these boards, and once everything is fine, then you can connect to a vendor who will provide you with fabricated sensors with embedded logic that you want. Correct? So many such development boards are available. The popular among the ones are listed here: Raspberry Pi, Arduino, Intel Edison, and these are the three quite common in some parts of the world. Actually, nowadays, though it's not mentioned here, Node MCU is very popular. It's a very cheap, it's like a replacement to Arduino, but with much more capabilities. So it's got wireless inbuilt, and you can use the same programming model as Arduino with that. It is very cheap, one-fifth the cost of Arduino. So Node MCU is one more in this list. And I particularly love Node MCU and I use it a lot. So this is how your Raspberry Pi looks like. This is a board, as you can see. I think some of you have already bought it. It is boxed but not opened it. When you open it, if it's Raspberry Pi 3, Model 3, 3 Plus, then it looks something like this. So very small board, and as I told you, it's a little bigger than a pack of cards. So very compact, but believe me, it's a complete motherboard. It's got everything to run as a full-fledged computer. So it's a single board computer. It's got a Broadcom SoC ARM processor, a GPU. Imagine it's got a GPU and 256 to 512 MB RAM. Actually, Model 3B Plus has got 1 GB of RAM, and the cost of Pi has remained always around $35. Then you can order it from many online stores. So Amazon and Flipkart and many others support that. It's a very common item. This is how an Arduino board looks like. It's basically an open source platform, and that's why it's become very popular and is used for building electronics projects. Though it is not a full-fledged computer, it's got a embedded operating system and you can flash it with your logic. But you can't have an operating system which you can program just the way we can see on laptop with it starts, and then you can do whatever you want. You can do programming in multiple different environments. You can't do that. Whereas in Raspberry Pi you can do that. So Arduino consists of both a physical programmable circuit board and a piece of software or IDE. So IDE is something that you can use on your laptop. So you have an Arduino IDE where you build your programs and then flash it on Arduino. Then this is how an Intel Galileo looks like. Intel Galileo is a much costlier and very robust board. So when you have to do some mission critical and those type of experiments, you'll use Intel Galileo. But otherwise, most of the times, a Raspberry Pi or an Arduino or a Node MCU should be good enough for any type of development activity. So choosing the development board. So which one would you choose? So although there are a lot of development boards that are available in the market at varied prices, but Raspberry Pi is supposedly most suited to start learning IoT. Features of Raspberry, it's useful for small or home-based business, perfect for adaptive technology. See, it's got, as we said, it can consist of multiple operating systems. So you can install Raspbian, which is a Linux version on that. You can install .NET Core on that. There are 4 or 5 operating systems you can install. You can use any of them. If you install Raspbian, you can program in Java, you can program in Python, you can program in Node.js, You can program in something called as Node-RED. Node-RED is again not a part of this curriculum, but I'll talk again and again because I want to introduce that subject to you all. You all will have any career in IoT, then you need to learn Node-RED. It is very, very easy. And if you want to do very fast IoT proof of concepts or demos for your customers or for internal business users, then nothing to beat Node-RED. I use it, and typically if a customer tells me they want to see something and I got just 1 hour, then Node-RED is the way I know I can build up something fancy into Node-RED and show it to them. So Pi can be coded in Python, I told you, Java, Node.js. You got few IDEs also on that. Couple of IDEs for Java, there are IDEs for Python, all available out of the box as a part of installed Raspbian base that you have. Current Raspbian install that you have, it's with that. It is energy efficient, which means it does not consume, of course, compared to an Arduino or a Node MCU, it consumes more power because it does much more. But then relatively it is very low. You typically what I use is I have a Android phone, and typically, your micro USB for these large smartphones works for this. So it requires a 1 amp adapter, which is used for charging your Android phone, micro USB adapter. Same thing can be used to power this. And biggest thing is you don't need any special license or anything. No, because Raspberry is free. So you can start experimenting without any hassles. So Ravi Kumar is asking, would knowledge of Node be required? Will it help in understanding Azure better, or we can do without Node? So Ravi Kumar, you can see it's not necessary to know any languages, but typically I would feel something like Python or Node is needed because today, in when you use some cloud technologies, there are a lot of things that you need to work out, and very quick and fast you can do in Node or Python. But even Java is fine, so don't worry about it. Only thing is pick up Python, because I see Node to be more useful when you want to do some beautiful GUIs, when you want to use something like Angular or React framework in Node.js. So they are all JavaScript frameworks. So that's where Node will be useful. So you can use complete full stack Python using Python Flask and Python at the backend. So if you're using Python, then better do that. So, and anyway, we are going to use Python. So if you focus on Python, you'll be much better off as you move along. And it is very, very easy. I know some of you guys are very experienced. So, for you, having done Java for such a long time, or any one language for such a long time, Python will be a child's play. A case of using it and getting the syntax and the basic libraries, getting used to them. So spending, I think, 30, 40, 50 hours doing some small applications, you'll be very, very comfortable with that. I told you the videos in the prerequisites are very good. And then there's a lot of material on the net available. You can go and search while you're doing it. And Python, in 10 minutes, you can start writing small Python programs. Abdul has a question. What are the boards that are used in real-time IoT development? Yeah, Abdul, that's what we talked about, right? So we talked about Arduino is one of the most common boards. I've seen Node MCUs like 1/5 the cost. So if you talk of Indian rupees, it is just 300, 400 rupees. You talk of US dollars, it's a $3 to $4 board. So everything that Arduino does, it does and gives you much more than that. That's Node MCU, NODE MCU, Node MCU. It's ESP8266 based board. So Node MCU, Arduino, Raspberry Pi, Intel Edison, BeagleBone, they're all the different development boards, Abdul, which are used for IoT development activity. So Raspberry Pi and its components. So I will skip this slide and let me straight away go to the video, because that video explains it in a better way. So this slide, don't refer this slide, because this slide refers to a little older version of Raspberry Pi. All of your Raspberry Pis will be newer one. So you'll get confused with this. Don't use this. Let me go to today, in today's session. If you see on the left side, description Raspberry Pi, this is this video I'm going to start. I'm coming to SenseHat, Parvesh. I'll explain what is SenseHat. So Raspberry Pi and SenseHat are two separate things. First, let us understand what Raspberry Pi. Then next, I'll go to what is SenseHat. So this is a small video. I'll play it and pause it so that we understand what are the components. So this is how your board looks like. I showed in a previous slide, not the last slide, the one slide previous to that. This is how it looks like. When you open up, it looks like this. Let me make this slide. Oh, this is not getting larger than this. Oh, it's getting. Okay. Yes. Are you able to see that? Yeah, very nice. You're seeing full screen now. Wonderful. There, so I'll start now. So this is how the board looks like. This is the main microprocessor chip. We talked about the Broadcom ARM CPU, correct? So this is that CPU. Then on the sides, when you turn around, this is the power socket. As I told you, this is a micro USB slot where you can use your, if you're using an Android or phone like that which supports a micro USB power input, same thing can be used to power this. Only thing you make sure that needs to be a 1 ampere, 5 volts, 1 amp adapter. So some of the older smartphones will come with power adapters which are of low capacity. They're 500 mAh or 700 mAh, so they run. But what happens is when you run for a little longer time, it consumes a little more power. It sort of hangs because the power supply is less. So better go for a 1 amp power adapter. So my current cell phone that I'm using Asus Android phone, which is coming with a 1.5 amp power so it's perfectly fine for this. And most of the last year or a couple of years, if you bought your smartphone, it will be larger. If it's 5-inch plus smartphone, it will be a larger adapter. So this is the HDMI port. So here is where you'll connect your monitor or your television. So you connect through an HDMI cable when you first time set up your Raspberry Pi. So one at the end of the HDMI cable will go to this HDMI port. Other end will go to your monitor. If you have a monitor and it supports HDMI, then you can use that. Or if you don't have, typically I don't have an HDMI monitor, so I plug it into my TV. So most of the TVs today, televisions will have two HDMI ports. So I plug it into any one of them, and in the other one, there are other devices which I plug in. And what I have done is, because my television is fixed to a wall, every time I don't want to bring it out from the wall, so I kept a cable hanging out from a HDMI port on the TV outside and remains hanging under my TV. So whenever I want, I just put my Raspberry Pi near that and plug in a Raspberry Pi. It's a very easy way, very handy way to do it. But of course, that you only occasionally need to connect. As I told you, after the first installation, you will not need that. You will use remote connection. I'll explain how to do that tomorrow. So this is the HDMI port through which you're going to connect. This is the audio video input output jack. Of course, we are not going to use it, but we would have heard people using Raspberry Pi as a media device using an operating system called Kodi, Kodi, Kodi operating system. So if you like challenges, then please go ahead and use that. And the best part is, this video goes ahead, you'll see the whole operating system here is installed on a micro SD card. So you can just plug in a micro SD card with a Raspbian, and you can have another SD card with a Kodi. So when you want to do your IoT experiments, you use the Raspbian SD card. When you want to use it as a media device, you put the Kodi in that Kodi SD card and then use it as a media device. Then you're going to use your audio video input output jack there. This is a CSI port. So it supports a camera also. And CSI port is a standard port where you can plug in camera. So you'll get cameras which support CSI port. So you can straight away using a cable connect your camera here. So your camera is straight away connectable to a Raspberry Pi. Then this is the DSI port. So DSI port is a display port. Your some display devices support DSI port, then you can connect it through that. Of course, we'll be using the HDMI because today most of the televisions have HDMI. So very easy to find that. Now, this is called the GPIO pins. GPIO port, there are 40 pins as you can see. So this is where you can connect your sensors, the input output pins. So sensors will get the input from here, and then there'll be some LEDs or some stepper motors which will take the output. So you can control a stepper motor or an LED again through G input output pins. Your sense head board also will be plugging onto the GPIO ports, and I'm going to explain what is sense head. Now we are turning on the sides. So as you can see, this is an Ethernet port. So Raspberry Pi supports both wireless and Ethernet network connectivity. So if you have a router in a home or office and you want to connect internet through that router, you can use an Ethernet cable and plug in, and you can be online. Or you can use wireless. So you have a wireless router, which I use, normally use wireless. You can connect wireless also. Now these are the four USB ports. So it's got four USB ports, and on the first setup, we are going to use two USB ports, one for a keyboard and one for a mouse. You'll plug in and you keyboard and a mouse into this USB port. The first time you'll require that. Till you take a remote control, you will need to. So you'll connect your monitor, you'll connect your keyboard, you'll connect your mouse, and then you power up, and then you'll use it as a computer like normal computer using your keyboard, mouse, and monitor. That's the first setup. Now this is the built-in chip antenna. This is what it uses for its wireless. This white colored thing, as you can see. Now when you turn it around, this is the Wi-Fi module, and this one, which is being circled, this is the micro SD card slot. So you see, it's on the reverse side. When you want to plug in, the slot is on the back of the card, and you have to, you know, insert your SD card here. So it's a micro SD card, and that is the memory. So you will typically have a 16 GB or 32 GB SD card. Don't go beyond 32 GB. So don't go for a 64 GB card. 8 GB is just okay, but I would prefer a 16 GB, because when you install Raspbian and you want to do something, then you'll be installing some stuff. So 8 GB will consume very fast. All your programs, operating system will reside on this SD card. So this is our Raspberry Pi. I hope you got what a Raspberry Pi is. So basically it's a motherboard single card computer where you can connect your monitor, keyboard, mouse, Ethernet or wireless, and start working, and you install your operating system on the SD card, which we're going to do tomorrow. I'll show you how to do that. And then you have full-fledged computer working. It's a 1 GB RAM machine, and it's a fairly decent, fairly powerful machine. So let's go back to the presentation. So we saw Raspberry Pi. Now let's go to the sensors part. So we saw what are sensors, correct? A device detects or measures a physical property and records, indicates, or otherwise responds to it. Sensors are the troops of the Internet of Things. The on-the-ground pieces of hardware doing the critical work of monitoring processes, taking measurements, and collecting data. So they are the eyes and ears for us, for Internet of Things. In the broadest definition, a sensor is a device, module, or subsystem whose purpose is to detect events or changes in its environment and send the information to other electronics, frequently computer processor. So what are the type of sensors? As you can see on the right side, different types of sensors could be position, presence, proximity sensor, motion, velocity, displacement sensor, temperature sensors, humidity, moisture sensors, acoustic, sound, vibration sensors, chemical and gas sensors, fluid flow sensors, force, load, torque, strain, pressure sensors, leaks, sensor or level sensors, electric, magnetic sensors, acceleration or tilt sensors, machine vision, optical, ambient light sensors. And a lot of these sensors are today available on our phones, like tilt sensors and some, GPS, a lot of other things. And these are only a subset of different types of sensors. In manufacturing industry, you'll find different types of sensors doing different type of things needed. Okay, so a lot of sensors are available. And basically, the job of the sensors is to convert the physical stimuli, which could be either the pressure, the motion, the position, the light, the temperature, the sound, the chemical. So it could be, some sensors are sensitive to our LPG gas. Some sensors are sensitive to our pollution. So, even then some sensors, you can identify the particles in the air. Based on that, they will convert that information to some electrical signals. So, these are the type of sensors. We saw temperature, proximity, all these we talked about. Ultrasonic sensors, the smoke, gas, alcohol sensor, touch sensors, color sensors. They can detect colors. Imagine. So there are something called as Raspberry Pi add-on boards, which are not coming with Raspberry Pi. So they are independent, separate boards to be purchased separately, and they are called hats. HAT hat. Their hardware attached on top. As you can see on the picture on the left, see below is a Raspberry Pi, and you're just plugging it a hat board into the GPIO pins. Okay, on the left side of that, the GPIO pins are there, and the hat has a plug which is fitting into the GPIO pins of the Raspberry Pi. And that's why they're called hats. Connecting through the GPIO pins. And they are add-on boards. So different type boards provide different features. Correct? And some major advantages of hats are no soldering, robust mechanical design, auto configuration. So I have a slide on auto configuration as you move ahead. So why it is auto configuration? So basically the concept is the head should start working the instant it is connected. The moment you plug into it, it should start functioning. That's the belief. The hats, all of the hats have an EEPROM, which is a small memory that has the details of all the hardware that it contains. So some list of hardware in a standard format. How does a Raspberry Pi know about that? So Raspberry Pi has specific two GPIO pins, number 27 and 28 pins. So when your hat plugs onto the Raspberry Pi, they plug into those two pins are connected to the EEPROM. Using those pins, it can read the EEPROM. The Raspberry Pi will be able to read the EEPROM on the EEPROM is nothing but electronically programmable read-only memory. Once in a while, electronically erase or program it, but largely it is read-only. So once you fix it, the content is not volatile, and it has got basic, very small memory, just a list of the hardware in a standard format. And the two pins on Raspberry Pi 27 28 helps to automatically detect and read that list. So these pins are reserved to connect to an EEPROM on the hat. So the EEPROM chip contains code in a .dtf file, which is known as the device tree, that outlines all the chips and hardware on the hat in a standard predetermined format, which is called .dtf format. So the moment a hat is plugged onto the Raspberry Pi and you put on the Pi, it detects that something is connected on the two pins, reads the DTF file, and discovers what hardware is attached. And then the Raspbian, which is the operating system, automatically loads the driver for that hardware. Correct? Sets up the GPIO pins accordingly. So without any intervention, your sensors are straight away connected to the Raspberry Pi. So hats were first introduced in 2014 with the initial Pi model. And since then, there have been fantastic hats available. The unicorn hat, there's a piano hat, beautiful, it's a nice thing. Just look on Google, it plays a piano. So it fixes on that. And you connect an audio device to the audio in output, and you can play literally a piano over there. Of course, there are a couple more. So Sense Hat is one of them. So there was a question, what is Sense Hat? So Sense Hat is one type of a Sense Hat, but it consists of something 5 to 8 sensors. Correct? Even there's an Explorer Hat. Explorer Hat is, you read, Google it out, but Explorer Hat, the Explorer which is circling around, it's a satellite circling around the Earth. It has got an Raspberry Pi with a specific hat created for that, which sends all the data that it senses and sends to the Earth. So it's actually doing some live sensing on the satellite and sending it back to the Earth. So this is how the Sense Hat looks. Correct? So Sense Hat is again an add-on board for Raspberry Pi made especially for the AstroPi mission. It was launched to the International Space Station in December 15. So, Sense Hat has gone there from where it is sending the data live. So what are the components on the Sense Hat? It's got an 8 by 8 RGB LED matrix you can see on this board, right? There's an 8 by 8 those square white LEDs. They're actually not white, they're multicolored LEDs. It makes beautiful colors. So 8 by 8, so 64 LEDs are there. Using that, you can create any type of a pattern or anything you want to display, any characters, you can do that. So let me do one thing. There is a video on this. Let me play that video also so that you understand what it is. A description of sensor. See, this is, I mean, of course, you don't need to know, but these are small chips on that. Each of them are different sensors. It's an accelerometer, gyroscope, and magnetometer sensor on this chip. This is a humidity sensor. So you may not be able to read clearly on the board. Of course, there is a dialog small which is showing you that. But if you look at the board carefully, you'll see that you'll read there is a humidity is mentioned there also. This is a temperature and a humidity sensor. This is a barometric pressure sensor. And the size of the board you can judge from the fingers that are holding it. So this is a pressure sensor. This is a 5 event joystick, so you can even use it to play some games or take some inputs from the joystick. This is an white 8 by 8 LED matrix which I talked about. This is the plug-in which plugs into the GPIO pins. These are again 40 pins. So that's the sensor. So it's basically a board, and by the name hat, hardware attached on the top. So it just plugs into the Raspberry Pi. It's got the gyroscope, accelerometer, and other sensors. Head can be connected to all other boards other than Raspberry Pi. Like, no, Abdul, they are specifically made for the Raspberry Pi. Of course, you can connect it, but not as a plug and play like Raspberry Pi. So your Arduino or a Node MCU also has got GPIO pins, but the order of the GPIO pins may be different. Also, their embedded operating system won't be recognizing or querying the EEPROM on the sensor. So it won't be able to automatically decide what hardware is there. So you can connect it through the GPIO pins and the GPIO pins here, but then your logic which you have flashed on the Arduino or Node MCU, you'll need that logic to query the sensors for the information through the GPIO pins like any other sensor. So SenseSat, as you can see, has got a gyroscope, accelerometer, magnetometer, temperature bearer, and you can simply plug in. Now the question is, do you need to buy this? So it's your call. You may, if you want and you want to buy, you're fine, because it's a nice board. You can experiment with it. But if not, then it's not necessary, because everything that you can do on the board, I'll show you. Raspberry Pi has got an SenseSat simulator also. So when we do the installation process tomorrow, I'll show you how to access the SenseSat simulator, and you can simulate a SenseSat connected to a Raspberry Pi, just like an actual board. Only thing is the readings will be simulated. Here the readings will be actual. That's it. Okay. So your call, not necessary to buy. But Raspberry Pi, yes, it is necessary to buy, because all our Python programs that we are going to run are going to be run on that, and you won't get the feel. So you can do some of the programming on your laptop, but then you won't get the feel of how you're working with sensors and embedded systems. So that's why it's very important that you have that. These little technical specifications, of course, you can go through that. Not necessary for you to know. This is only technical, like if you want to see that, otherwise fine. So a significant feature of HATS is the inclusion of system that allows the B plus, which is a Raspberry Pi B plus onwards boards, to identify connected hat and automatically configure the GPIOs and drivers for the board, making life for the end user much easier. So anyone who has done this type of programming, anyone who's connected some different sensors. So like I have a Node MCU and I have connected a few sensors. I have connected a GPS sensor to it. I connected a temperature and humidity sensor to it. But you need to do a lot of work. Small programs you need to, at the lowest level, you to do to get the data from the sensor. Whereas in Raspberry Pi, when you connect this type of hat boards, all that work is out. You can straight away start working. Okay, the moment you fix it, that's it. So we'll start the configuration in the next module. So until we try to identify IoT devices you come across in daily life, try and figure out different types of IoT use cases. I talked about a couple of cases today. We'll talk about a lot of them as we move along. So now, before I go for the quiz, let me tell you what you need for tomorrow. So this is to set up a Raspberry Pi. What are the things you will need? I believe you can see my desktop. Yeah, I'll make it a little bigger. So, first of all, you will need a Raspberry Pi 3 Model B Plus. You need a power adapter. It does not come with a Raspberry Pi, though there are some vendors who sell a kit like thing. So power adapter, which is micro USB, it's got a micro USB input. So just like your mobile smartphones, and minimum 1 amp. So 5 volt 1 amp you should go. Don't go below 1 amp. Higher than 1 amp is fine. Then you need a TV or monitor, which you'll connect to an HDMI cable. So you'll need a HDMI cable, connect from Raspberry Pi to the TV or monitor. Or like I have an old LCD monitor which supports VGA. So if you want to use that type of a monitor, then there are adapter cords available, VGA to HDMI. So what I do is I connect that VGA to HDMI cable from my monitor. So monitor side has a VGA, the other side of that cable is HDMI. So this adapter converts VGA to HDMI, or rather the other way around, HDMI, because it's a display, right? So the HDMI from the Raspberry Pi, it converts into VGA, which my LED can display. So Hari says he has wireless keyboard and mouse. Wireless keyboard and mouse also works. So you have to connect to the USB. So I've used them. So your USB connector, you connect to the USB ports, and then you can use that. No issues. So Deepak has a Pi 2 Model B 1 GB. Deepak, there'll be, so Pi 2 has got some of the, so even I think GPIO pins it doesn't have 40. And at some of the areas, I think it does not have Bluetooth also, and I'm not too sure about wireless also. But it has got some limitations. So you may fall short and you may have to do a little more. So I would suggest if you can go for Model 3 B Plus, you will do everything that we're going to do. So Harigunda says dongle, yes, the USB mouse or USB keyboard, correct? Wireless mouse or wireless keyboard will have a USB connector, right? So connect to the USB port, should work. I'll say Raspberry Pi 3 Model B Plus, and you will see all the Amazons of the world. They are showing you with the prices of this. This is because I'm in India. It is showing me prices in India. So these people, even Amazon, all other sites will show you can go and buy it from there. Again, but go and see there because they'll have different types of things. There'll be many other things they'll go and sell there. You can buy this from anywhere. A lot of sites. There are a lot of local folks who are selling them. So there are within India, I know a lot of for each of the city will have an area where you get electronics devices. You just go for a walk into that lane and you'll find people selling Raspberry Pis there. Or better still, order online. I think Amazon now delivers within a day or two. If you're a Prime member, then within 2 days or even 1 day. So buy it from any of these things and that should be fine. Coming back to my, so you'll need this TV monitor. I showed you what you need. Micro SD card, I would suggest to go for a 16 GB or max 32 GB. Don't go below 16 GB if you have 16 GB, but it's a micro SD card. Okay. And yes, and you need a mouse, you need a keyboard, and this is only for the first time. So I mean, if you don't need it every time, so if you can borrow from a friend, if you don't have, then borrow it. Of course, otherwise maybe once buy it if you don't have, because you need it first time to set up. And then you have to download something called a Raspberry Pi Noobs. So I'll show you where to download. You just search on Google Raspberry Pi NOBS. So there is a site. It's a Raspberry Pi site, and Noobs is a short form from new out of the box software. It's a complete bundled Raspberry into that. In that you see on my screen there are two things, Noobs and Noobs Lite. So install something called as Noobs, not Noobs Lite. Okay. I think it'll be around between 1.5 to 2 GB. So download the zip and tomorrow I'll show you the process. Of course, you won't be able to do the whole installation while we are discussing, but you have everything ready. Then after the session you can go and install it. Okay. So let's get back to our slide deck and let's get into the quiz. So what makes IoT a leading technology? A, B, C, D. Type in the question box. High computing capacity. And as we saw, one of our friends was doing certain things, 6 to 10 years back also. And I dabbled into electronics at the start of my career. I played a lot with microprocessors. But at that time, 8080, 8085, Z80, those are microprocessors. They were very costly. They used to do much little. They consume more power. Today, high computing capacity, everything is available. And that's why IoT is really come to the center stage. What is a key property a thing should possess? Very easy, I believe. Key property that a thing should possess. What is the main requirement from a thing? A thing, correct? It is to capture data. That's the base stuff. Major properties of an IoT device: sensing, computing, communicating, all of this. Really, that makes me happy. At least I'm sure you didn't sleep. Thanks for that. A thing can also be a virtual object which generates data. True, false. Answer that. But the real answer is true, that yeah, in a lot of situations you want to simulate. And why you need simulation? And this we didn't cover, so don't worry if you got it wrong, because a lot of times when you're doing development, let's say depending on a blueprint, we saw that blueprint architecture, the 5 technology stack and the 6 decision areas. you will decide that I need this data, this my sensor should send. But when you define that based on the business goals, you won't get a ready-made sensor available to you off the shelf. You'll have to start looking for a vendor. Vendor will have it ready. You may have to fabricate. It's a long process. Sometimes it's fast, sometimes it's slow. But your development can't stop. So you'll start using simulators. Simulators exactly mimic the actual sensors so that your development activity starts, and then somewhere along the way your actual device comes. And actually I'm working with a customer today where we are working a connected car solution. They are nearly completed 70% of the application solution today. Their real device is now getting shipped. Just yesterday we got a message that they're shipping it, because we had a lot of chit chat of to and fro. No, this, I want that. This is a feature I don't want. This is the embedded software. The software should do that much. This is the data that should come. So all those decisions in the device needs to go, and it takes a lot of time. That's why simulators are used, right? Like we'll see the Senset emulator in Raspberry and tomorrow. So summary, what we did, what is the Internet of Things? What's difference between IoT and M2M? We saw the solution reference architecture, the four-stage information flow. We saw the development roadmap, the architectural blueprint. We saw the various development boards. We saw why we selected Raspberry Pi. We saw Senset boards, right? So covered a lot of stuff, lot of ground today, but I did a lot of talking with not too much of programming. You'll enjoy a lot more when we do programming, but I believe just as I enjoyed the session, you enjoyed the session, and I definitely believe it's informative for you guys. So with this, we can end the session today. Don't forget your feedback, and you're free to leave for today. Thank you. Bye bye.